So, lesson 4 of the P2 topic. The story so far. Hopefully, you've watched the introduction. You recognise this. We started with speed and velocity, speed being a scalar, velocity being a vector, and the equations. Then we did the acceleration equations. Acceleration is v minus u over t. Got to remember that one. And v squared minus u squared equals 2as. Don't worry, you get that one in the exam. Then we looked at graphing speed and acceleration and how we use a velocity time graph for acceleration and a distance time graph for speed. And we related the gradient to the speed and the gradient to the acceleration. And a cheeky little bit at the end, we learned that the area under a velocity time graph told you the distance travelled. And that's where we ended. So today, Newton's 3 laws of motion. So let's dive straight in. Newton was interested in lots of things. He came up with a prism, saw light being dispersed. He invented the cat flap, apparently. He worked for the Royal Mint. And one of the things he's supposed to have done is sat under a tree, and one day an apple falls and he gets an insight into the idea of gravity. And out of that, he distills 3 laws of motion. You've been doing these since year 7, so none of this is going to be a massive revelation for you. But let's make a start. So, number 1. All objects will keep moving. So, we call them bodies. I forgot which way the D goes in. All bodies at rest and motion stay at rest or in motion unless an unbalanced force acts upon it. Not farce, force acts upon it. I'm just going to, because I just realised my grammar's not great here. Rest stays at rest. If it's already moving, so in motion, it stays in motion. Okay, it's not that rest starts moving and a moving stops. Okay, so what does it mean in real life? It means that if you're sat there on your chair, and you might remember this from year 8, so we've got you sat on a chair, and if you remember, I'll probably put you on some wheels like that. There are forces acting upon you. Now, forces are a vector, and that means we draw them as arrows. So if I was to draw these, if you're sat completely at rest, well, completely at rest, you wouldn't have these. However, you would have 2 forces acting on you. One of them is weight. We look at that a little bit more next lesson, and that is in newtons. But all the atoms in the chair are pushing back on you, and in the wheel, they're pushing back. So we add all that up, and what we find is we have an up thrust. We would call that a reaction force. It is a force that is reacting to you sitting on the chair. And as long as those are balanced, so in this case they're balanced, you will remain at rest. Now, what about if we come along though and we start chipping away at here? We use a saw. So, I don't know, try and draw a saw. Got a saw, and we start sawing away. So this bar here can no longer push back upwards. Well, what would happen? Well, this force would go, because it couldn't push against you anymore. You'd be left just with this downward force. Boop. And so you would then become in motion. So you would no longer stay at rest. You would then accelerate. And if I was teaching you, I give a really nice example of this. It's one of my favourite little practicals. I get 3 balloons. So we get 3. In fact, I'll try and draw them as balloons. God, I'm well out of... Let me have a go. Balloon. Nope. One more go. That'll have to do. Okay, we'll do that. So we take 3 balloons like so, and I may have shown you this in year 9. I'm supposed to only do it in year 11, but I like to cheat. And I take 3 balloons like so. And we'll have the 3 colours. We'll have nice blue. And we'll have a nice purple, lilac colour. And we'll have green. Okay, so I've got my 3 balloons. And to each one there's a piece of string. The first 2 I create unbalanced forces. On this one I put too much blue tack on the bottom. So what I end up with, I'm going to choose a thicker pen now so I can draw arrows. I'll choose that one. I'll do them in purple. So in this one I have a greater downward force. The weight is larger than the upthrust coming from the, I'll write this one out, from the change in density of the gas, hence it floats. So these are helium-filled balloons, by the way. So in this one, I end up with what is called a resultant force. And if, for example, this was, let's keep the numbers really simple, 2 newtons, and this was 10 newtons, then I end up with a resultant force, downwards, of 8 newtons. And we call that the resultant. It's what's left over when you take 2 away from 10. Then on the other one, we take off the blue tack. So we would get something like small weight, and we'd imagine, I don't know, for some reason this one's a bit bigger. I'm just going to put UT for upthrust, keep it simple. And in this case, if the numbers again were swapped, 2 newtons, let's put this one in at 7 newtons. We'll mix it up a bit. In this case, what we'll end up with is 5 newtons remaining. So there's my resultant. And in both cases, the balloon's going to move. In the first one, the balloon's going to obviously move downwards because there is a resultant force downwards. And in the second one, the balloon's going to move up because there is a resultant force upwards. So here we have 2 examples of, if we do that to them, these are unbalanced forces. That causes, it creates acceleration. Okay, so they would remain at rest, however they have unbalanced forces acting upon them, which causes them then to not remain at rest, in this case accelerate. The third one though is always my favourite to try. It's the trickiest, and it's where I try and make the weight, I'm going to go for 5 newtons, and the upthrust completely the same. A real nice example then of Newton's first law in action. So if I have upthrust of 5 newtons, downwards weight of 5 newtons, well, what I end up with is a resultant of 0. And if you get this exactly right, what you end up with is stationary. Because, that's terrible writing, I'm at the edge. It's stationary because the forces are balanced. And it's weird to see, it's very rare to actually see floating things in completely balanced forces. Doesn't happen often. Usually the upthrust is greater and it'll fly away, or it's too heavy and it'll sink. So to get it exactly right is a bit of a novelty in my lesson. The other thing is, and this one's counterintuitive, if you already start the balloon moving, it carries on at a constant speed. You get a bit of air resistance which messes it up in the long run. But for a few centimetres, a few seconds, it'll move just at a constant steady speed. So it'll be stationary. Let me just move. Let's put balanced where it should be, really, at the top. It's balanced, which causes it to be stationary, or if already moving. Remember, you can pause this at any time. If already moving, to stay at a steady speed. At a steady speed. So these three balloons really nicely demonstrate Newton's first law, that an object will remain in motion or an object will remain stationary unless there is a resultant force acting on them, unbalanced forces, in which case it will then go in the direction of the resultant force. So that's the first law done. Next law, second law. Second law is an equation, nice and easy one. Force acting on an object, which is measured in newtons, is equal to mass of the object, kilograms, times the acceleration acting on the object, meters per second squared. So what does it mean in real life? It means take a ball, kick the ball by applying a force, the mass is the ball, and lo and behold, the ball will accelerate away. So it's the most fundamental rule really in physics that we come across, that if you hit things, they move. And if you hit them a bit bigger, if you apply more force and it gets bigger, well, surprise, surprise, it moves quicker. Whoop. And if you make it heavier, so I don't know, try and kick a medicine ball, funnily enough, the acceleration will go down because it won't move as fast. So that's Newton's second law. It goes nicely in a triangle. We can pop it in if it would draw one, try again. And again. That'll do. So we can put it in a triangle, and we can go across, and we can go F equals MA. And remember, we cover up the one we want, we say what we see. So F equals MA, but we can cover up the M and have M, and that would be F over A. Or, if we were given F and M, we could be given, find the acceleration, we do force divided by mass. We just plug them in. That's really it for the second law. F equals MA. It's just memorising it, and you will be needed to memorise it. The third and final one. Third law. If we go back to that example again of you sat on a chair, even laid on your bed, wherever you are while you're watching this, if you've managed to stay awake. If we sit on a chair, for example, so, I don't know, say we've got one with stools, legs, there we go. Really short. Wow, there we go. Then Newton's third law says for every action, now an action in this case is you pushing down with weight. So I'm going to do it from there. By the way, this point here is the centre of mass. And when we're drawing mass diagrams, I was naughty earlier, I didn't do it. You draw from the centre of mass, which on a human being is about where your belly button is. For every force, so in this case, weight pushing down, the chair is pushing back. There is an equal and opposite reaction. So here we have the upthrust, which is a reaction force. And I've written this above already. Reaction force. In reaction to the weight. Now there's a couple of others, like seeing the new exams, I've seen two of them now. The one that caught a lot of people out last year was an actor acting from wires to pretend to be flying. So the actor's hanging off the wires, there's the wires on the harness, and the person's, oh my god, wow, looks like, I don't know what that looks like, it's awful. Professional pride says I must do a better job than that. Okay, let's try that. Right, so we've got an actor, they're hanging off the wires, and they say the person isn't moving. So question number one actually was, what is the name of the force in the wires? Because the person has weight, so draw it from their belly button. What is the force in the wires? And the reaction force this time is called tension. And the tension arrows are upwards, because they're equal and opposite to the person, because the person isn't moving. They then give you the size of the downward force. So they say the person has a weight of 700 newtons. There's their weight. So the question then is, how much force is in the tension? Or what's the tension force? And because they're equal, the answer was 700 newtons. And quite a lot of people in the exams got hammered by that, so it's worth mentioning. Another example might be, you might have a wall and you might have a ladder against the wall. Oh my god, that is awful. Anyhow, you get the idea. Ladder up against the wall, and the ladder is sliding out that way, but friction is pulling it in that way. And as long as they're balanced, the ladder stays put. If you go obviously too far the wrong way, let's see if I can grab that. If you go too far the wrong way, then obviously the force this way is too big, friction can't keep up, and the ladder will collapse. But that's where you want to get it at the optimum angle, like so. So here we might have sometimes you just got to call it a push. Here we have a push, and here we have friction. So yeah, for every force, there is an equal and opposite reaction force. So we'll finish on that. I realise I haven't written it. For every force, there is an equal and opposite reaction force. So keywords on that one, definitely equal and opposite. For every time you push forward, there's a frictional force on your foot pushing back. Whenever you sit on something, the force pushes back. And whenever that can't be balanced and equal, you then end up with a resultant force, and then stuff happens. So the seat breaks, the tension in the wire is not enough, and it snaps, and the person falls and accelerates. The ladder can't push back, and so then you end up with Newton's first law. Things remain in motion unless an unbalanced force acts upon them, and in which case you're going to go flying. So that's Newton's 3 laws of motion. You're expected to know them. I have seen questions where they explicitly ask you, what is the third law? What is the first law? So practice them, test yourself on them. As always, leave something in the comments if you're stuck, or contact me on rw@mullionschool.org.uk. And if not, I'm assuming that you're doing okay. Take care. Bye.